thank you to the organizers for giving me the opportunity to speak here and to present some work that I submitted last August about how you can count BPS states that carry a charge under discrete symmetry in M theory. So let me start right away with some motivation. As you well know, BPS states provide us with one of the most important lampposts with that we can probe non-perturbative physics in string theory and supersymmetric theories in general. Now, one of the striking applications in recent years have been quantitative verifications of several swampland conjectures in Calabi-Yau compactification. In particular, for example, in the context of six-dimensional theory, studying the elliptic genera of non-critical strings, and also after circle compactifying in the five-dimensional theories, where you then get indices of five-dimensional BPS particles. So I apologize for not citing any of the swampland literature, which is of course, dauntingly vast, but I'm sure you know all of the relevant players. So my point is that in all of these studies, focus has been on theories with only continuous gauge groups. And you can ask yourself, what can we actually learn from theories that also have a discrete gauge symmetry and BPS stage, which are charged under the symmetry? And in this talk, I actually want to not answer this question, but to take the very first step and ask, how can we even calculate such spectra in the first place if we have discrete charges in M theory on a Calabi-Yau threefold? So let me start by giving you some background and considering just having a smooth Calabi-Yau threefold, no discrete symmetries inside. And then you get a five-dimensional effective theory from M theory with BPS particles that arise from M2 branes wrapping curves in this Calabi-Yau manifold. You have a massive little group of SO4 in 5 dimensions, which decomposes into two SU2 factors. And then you can label the multiplicities of these states by the spins and also by the U1 charges, which take value in the curve lattice of the Calabi-Yau. Now, in the presence of gravity, compactifying on a compact Calabi-Yau, these numbers actually depend on the complex structure of the Calabi-Yau. So what one usually does is one studies an index that is independent of this complex structure deformation by tracing over the right spins. And what one that gets is the famous Gupa-Kummer-Waffer invariants that have been found by them in 1998. And as you also probably know, is that they are encoded in the topologic string partition function. So since this will be quite important for the talk, let me briefly show you how this encoding works. So the topologic string partition function is denoted by Z top here. We take the logarithm in order to get the free genus expansion. And then we first of all have a sum over three ranges. The first is a sum over charges, namely curves in the Calabi-Yau. The second sum that we have is over worldsheet genera of the topological string. And then we also have a third sum, which is over multi-covering contributions of two branes, but this will not really be important in this talk. It just tags along. And then you have in this expansion the actual Gupa-Kummer-Waffer invariants, NG beta. You have a factor which contains the topological string coupling lambda and also takes into account this multi-covering contribution. And then the expansion parameters are actually exponentiated complexified Kähler parameters. So these measure the value of the Kähler form and the B field along curves in your Calabi-Yau. And this topologic string partition function can be calculated using numerous ways. In the compact case, for example, via mirror symmetry, the modular bootstrap, or localization calculations. And then in the non-compact case, you have even more possibilities, for example, the topological vertex and so on. Now, this is the story about continuous symmetries. How can we get discrete symmetries and how do we count the corresponding states? Again, I will start with a smooth Calabi-Yau threefold. And on a smooth Calabi-Yau threefold X, it's known that a discrete gauge symmetry, a Zn gauge symmetry in M theory, arises when you have torsional 3 cohomology or dually torsional 2 homology. So torsional curves in your Calabi-Yau. And then discrete charged particles arise from M2 branes that wrap these torsion curves in the Calabi-Yau. And it's also, it has been conjectured how to generalize the Gupa-Kummer-Waffer expansion in order to encode the indices of BPS particles with different charges. And Dedushenko and Witten have proposed the following expansion. You have the same sum over curved classes, but now beta can contain torsion contributions. You have a sum over genera and so on. Again, the label beta includes the discrete charge. But then what changes is that each contribution is weighed by the value of a homomorphism from the curve lattice into the roots of unity, which encodes the choice of a flat B field that you can turn on along this torsion curve in type 2A string theory. And the idea is that if you now compactify topologic string on X and you turn on this B field, then the corresponding partition function that you get encodes the discrete charge invariance in this way. So now you could ask, everything is known, so why do I give this talk in 2022? But of course, there's a catch to the story. And the catch is that this formula has actually never been applied. And I think there are basically two reasons to this. It's easy to see that to use this formula to extract the invariance, you actually have to know the topologic string partition function for every possible value of B field that you can turn on along these torsion curves. And it's actually not really known how to calculate these quantities. So the only example of a calculation that goes in that direction is actually from 2007, where they perform brutal calculation in a series of 2 papers to get some genus 0 instanton numbers on a Calabi-Yau with torsion curves. So it's not known how to obtain these partition functions in general. And the second problem is that most of the examples that we have of M-theory compactifications with discrete gauge symmetry actually do not come from a smooth Calabi-Yau with torsion cohomology, but they come from a singular Calabi-Yau manifold where this notion doesn't really make sense. So I will argue in this talk that these two problems actually conspire together to have a very elegant solution that I want to present to you. Now, let me tell you how you get these discrete symmetries from a singular Calabi-Yau manifold. And to this end, I will now assume that we have an F-theory lift. So the Calabi-Yau has an elliptic vibration, and the corresponding 5-dimensional M-theory vacuum is actually the circle compactification of the 6-dimensional F-theory vacuum that is encoded in this Calabi-Yau. Then it is known that the discrete gauge symmetry in 6 dimensions corresponds to the so-called Tate-Schaffer-Ravage group, which is a somewhat scary mathematical object. But the way I want you to think about this is just to consist of all the torus vibrations that encode the same F3 vacuum. And what is important is that it always contains exactly one elliptic vibration, which means a vibration that has a section or a map that embeds the base into the vibration almost everywhere. This is called the Jacobian vibration. And all of the other geometries do not have a section. Now, the second important fact is that a non-trivial Tate-Schaffer-Ravage group implies that this Jacobian will be singular if X is a Calabi-Yau. But it is also known that only on the Jacobian vibration does M-theory preserve all of the discrete symmetry in 5 dimensions. So from this perspective, we are forced to really study M-theory on singular Calabi-Yau manifolds in order to get discrete charge BPS particles. Now, to understand this a bit further, let me explain to you how this discrete symmetry arises via Higgs transitions in F-theory and in M-theory. So from general quantum gravity arguments, it's assumed that every discrete symmetry can be embedded into a abelian or into a continuous gauge symmetry and arises via a Higgs mechanism from this continuous symmetry. And now in this example, we consider a Tate-Schaffer-Ravage group, which is Z2. It just contains a smooth genus 1 vibration, a smooth genus 1 fibered Calabi-Yau threefold X, and the associated singular Jacobian vibration J of X. And then a third geometry comes into play, which is a torus fibered Calabi-Yau threefold that leads to this U1 gauge symmetry in F-theory. Now in F-theory, we compactify on Y, we get a U1 gauge symmetry. In the spectrum, we assume that we have a hypermultiplet of charge 2. We give the scalar in this hypermultiplet a VEF, and this breaks U1 to Z2. And this Z2 you obtain equally if you compactify, so to say, F-theory on X or J of X. But in M-theory, this is a little bit different. After compactifying on a circle, you get an additional Kaluza-Klein gauge symmetry. And then you have the additional choice, which Kaluza-Klein charge gauge field is supposed to have. So on the one hand, the inequivalent choice is that you have U1 charge 2 and KK charge 0. then indeed you break the U1 to a Z2 gauge symmetry in 5 dimensions, and this corresponds to M theory on the Jacobian vibration. But the second option that you have is to perform the Higgs transition with a Higgs field that has U1 charge 2 and Kaluza-Klein charge 1. And what then happens is that the unbroken gauge group is actually a mixture of the U1 and U1KK, which is again a U1, and there's no discrete symmetry anywhere inside. And these two compactifications differ by a Wilson line that you can tune in order to adjust the masses of these Kaluza-Klein states such that one or the other of these states becomes massless. So this is why in M theory, only on the Jacobian vibration, you get the discrete symmetry. Now, let me talk a little bit more about the elliptic genera of the strings that you have in these theories. So if you're just interested in the massless spectrum of the F theory compactification, be it on J of X or X, then it is usually sufficient to study the smooth genus 1 vibration X. And from this, you can actually extract the information about the massless spectrum in F theory. But this is not true for the full 5-dimensional BPS index. What you can do, for example, is you can take the topological string partition function, and this admits an expansion in terms of the elliptic genera of 6-dimensional strings. So these are traces of the form that you see here. And what we actually want to know now is this index, but where we only trace over the subspace of the Hilbert space of Zn charge K. But again, this is not encoded either in the partition function of the smooth genus 1 vibration or in the partition function on the singular Jacobian vibration, at least not directly, as you will see. So to make progress in this problem, let us rewrite it a little bit. Equivalent information is actually encoded in the following index if you trace over the full Hilbert space, but now you insert the following operator. You take an nth root of unity, mu n, and then you exponentiate it by k times p, where p measures the Zn charge of a state. And if you know this trace for each value of k from 0 to n-1, then you can again extract these traces over the subspaces of the Hilbert space of discrete charge k. And what I argued for in this paper from last August is that this trace with insertion of mu n over kp is actually encoded in a topological string partition function, but of certain non-commutative resolutions of the singular Jacobian vibration. So the expansion looks structurally very similar to the one by Dedushenko and Witten. Here you have a sum now over the discrete charge, the Zn charge in this case. The invariants are labeled by beta, which are curve classes without torsion, and q, which is the discrete charge. And you have this nth root of unity exponentiated by m times k times q, where q is the discrete charge. And again, if you know this partition function for each value of k from 0 to n-1, you can extract these invariants. But again, the interpretation is that this is actually the partition function on the singular Jacobian vibration, where we have turned on a fractional B field localized at the singular points, which stabilizes the singularities and renders the string theory compactification smooth. And this, in a certain sense, can be interpreted as a non-commutative resolution of the Jacobian vibration. So let me explain this term a bit more, what a non-commutative resolution is supposed to be. So this is a way to get smooth string compactifications in a sense without resorting either to classical geometric means of blowing up or deforming. And a classical example are orbifolds which allow for discrete torsion. So it was already noticed in the 90s that if you have a string on an orbifold m divided by group gamma, and you have this cohomology group non-vanishing, then you can turn on a degree of freedom on the worldsheet, which then obstructs the deformations that would remove this orbifold singularity. And this has been subsequently interpreted as a choice of gamma action on the B field, or in some sense, you can also think about it again as a B field localized at these singular points. And then mathematicians have picked it up, or actually I'm not quite sure if Kontsevich was inspired by this or not, but in mathematics, the idea then came up to define resolution of a space just in terms of the sheaf category, which in string theory language would mean in terms of the category of branes on this space. So the idea is you have a singular space, but to the perspective of a brane propagating on the space, it can still be smooth. And while on a smooth space, topological D-branes take the form of complexes of modules over the structure sheaf, which is locally commutative algebra on the Calabi-Yau. Now the D-branes become complexes of modules over non-commutative algebras, which motivates the nomenclature of non-commutative resolution. So in the context of the singular Jacobian vibration, it is known that the Jacobian vibration has singularities which are so-called Q-factorial terminal. This means that you cannot blow up these singularities without destroying the Calabi-Yau property. But what you can actually do is to perform a so-called small analytic resolution, which preserves the Calabi-Yau property, but it destroys the Kähler property. So pick your poison, it seems. But a certain derived equivalence of D-brane categories in string theory language motivated Calderaro in 2000 to conjecture that the sigma model on a certain small analytic resolution of the singular Jacobian with the B field turned on actually flows under RG flow to what one could call a non-commutative resolution of the Jacobian vibration. But again, this conjecture has not really been picked up since then. So now that I claim that in order to extract the discrete charged invariance, you actually have to consider the topological string partition function on all of the possible non-commutative resolutions of this Jacobian, you are of course tempted to ask if we have actually gained something. But before I come to that, I just remember that I have some pictures to illustrate how this actually is supposed to look like. So sorry for that. The idea is that we have a singularity here, Q factorial terminal, somewhere in your Jacobian vibration. We now perform a small analytic resolution that destroys projectivity or destroys the Kähler property. But this provides us a torsional two-cycle that we can use to turn on a B field. And we then shrink it back to a point and hope that we can get away with it, so to say. And having this intuition, let me argue, or let me show you how this actually leads to a very straightforward way to obtain the relevant partition functions that we are interested in. Now, again, considering the easy example or the simplest example of a Tate-Schaffer-Ravitch group, which is Z2, and remember that we had this unhixed geometry denoted by Y, which leads to a U1 gauge symmetry in F theory, we can then consider the associated elliptic genus of a string, for example, and we can refine it with respect to the U1 charge. So we introduce this fugacity zeta exponentiated by the U1 current. And here the parameters are Q, which is the exponentiated complexified volume of the generic fiber, and theta, which is the exponentiated complexified volume of isolated curves in the fibers. And the imaginary part of M actually parameterizes the mass of the Higgs field that we are interested in, so to say. So if we want to perform the Higgs transition that leads us to the Jacobian vibration, what we have to do is to set M equal to 0, shrink the curves, make the Higgs field massless. And indeed, if we take this elliptic genus and we just set M equal to 0, what we get is the elliptic genus associated to the singular Jacobian vibration. Noting that the singular Jacobian vibration is complex structure deformation equivalent to the generic elliptic vibration of the same base, and therefore should lead to the same expression for the elliptic genus. Now, in order to get the smooth genus 1 vibration, we actually have to tune the Coulomb branch parameter relative to the Kaluza-Klein scale, so to say. And in this example, we actually have to send M to tau half, or equivalently, we set tau to 2 tau and M to tau. Then we get this elliptic genus of the smooth genus 1 vibration. But now, thank you. In order to get the partition function of the non-commutative resolution, we do not set m to 0, but we set it to 1/2. And if you remember, it's b plus iv. What this means is we set the volume of these curves to 0, but we leave a fractional 1/2 b field turned on these shrunken curves. So this is exactly the picture that I just showed you, resolving the singularity, turning on b field, shrinking it back to 0 size. And you do not even have to resort to the Higgs transition in order to obtain this quantity, because if you now look at the modular transformation properties of elliptic genera, you find that the partition function on the smooth genus 1 vibration and on the non-commutative resolution of the Jacobian vibration are actually related by a Fricke involution. In more general cases, you find Aitken-Lehner involutions. And now, together, noting that the partition function of j of x is the partition function for k equals 0, the trivial non-commutative resolution, so to say, we have all the partition functions that we need in order to extract the discrete charged invariance in this case. So let me give you a very quick toy example to show you some numbers. So you can take the E string, you can geometrically engineer a genus 1 vibration that essentially embeds the Z2 discrete symmetry into the E8 flavor group. And then you can look actually at refined Gopa-Kummer-Waffer invariants, which have the full dependence of the left and right spin because we have decoupled gravity. And then for the E string, what you get on the left hand, what you get is on the left-hand side. Here we have set all flavor masses to 0 and just keep the information about the dimensionality. And now if you calculate the Z2 charge 0 and the Z2 charge 1 states, what you get is exactly the splitting of each of these representations that appear, or the sums in the sums, into SO16 times Z2 representations embedded in E8. Now, before I wrap it up, let me comment also on the picture in the stringy Kähler moduli space. Now, this Fricke involution relating the partition function, of course, it's, how to say, you can use it to obtain the respective partition function, but it actually turns out that the partition function or the large volume limit of the non-commutative resolution lives in the moduli space of the smooth genus 1 vibration. So here I show you the GLSM Fi parameter space associated to a smooth genus 1 vibration with the 2 section, which provides an approximation to the actual stringy Kähler moduli space. If you go in the upper right corner, you find the large volume limit associated to the smooth genus 1 vibration. But then what the Fricke involution does is it brings you from the large volume limit to the small fiber limit. So you are moved directly into this phase boundary between a hybrid phase and the geometric phase. And this is where the large volume limit of the non-commutative resolution lives. So one interesting thing to note here is that the small fiber limit is essentially the F-theory limit. So this is very speculative, and I do not have a definitive answer to this question, obviously, but it at least raises the question if the B field actually lifts to 6 dimensions. So if you have a discrete degree of freedom that you can turn on to lift this B field, and of course, things that come to mind are perhaps T-branes that could provide such an additional degree of freedom. But again, at this point, it's really speculation from my side because I haven't really made progress in understanding this perspective very well. Now, let me also note that the network of geometries that are involved can get quite complicated. So here's just a sketch of the geometries that are involved if you consider vibrations with 6 sections. That you actually need to gather the partition functions that are spread across the modular spaces of 4 different smooth torus fibered Calabi-Yau manifolds. But it's actually possible to systematically engineer all of these vibrations that you need and then use Aitken-Lehner involutions to obtain all of the partition functions of non-commutative resolutions and to extract the Z6 charge invariant in this case as well. Now, before I end, let me briefly give you an outlook about some work in progress. So with Albrecht Klemm and Eric Sharp, we are generalizing this to geometries that do not have an F-theory uplift, so Calabi-Yau manifolds without a torus vibration. And this is also applicable in such scenarios, and we try to understand general properties of the topological A model on these types of non-commutative resolutions, then with Ji Gu and Paul Ullmann, we try to make this useful in the study of 6- and 5-dimensional superconformal field theories, analogous to what we saw for the E-string example. And of course, the picture of the network of geometries is taken from work in progress with Johanna Knapp and Emanuel Scheidegger, where we go beyond the 5-section case that we have studied last year and investigate geometries with 6 sections. So with that, let me finish my talk, and thank you very much for your attention.
All right. Thank you very much, Thorsten, for a very nice talk. Thank you with our clap emojis. Again, if you have a question, please raise your hand. I'll ask one while people think about questions. So the formula that you had where you sort of just took the partition function and you inserted, I think you called it mu, which were the nth root of unity to the kth power.
Yeah.
So does this generalize to non-abelian discrete groups by putting some character there?
You mean, that's a very good question. So I do not exactly see how. I do not exactly see how. And I also wouldn't know how you could then possibly generalize the modular transformations that provide you with the relevant partition functions. That would certainly be very interesting to investigate, but I haven't thought enough about the question of how you obtain non-abelian discrete symmetries in the first place to say anything meaningful or relevant about this at that point. So yeah, I apologize.
No, yeah, thank you very much. Are there more questions? Okay, I don't see any. So let's thank Thorsten again, and also Piri, our first speaker. And we'll end it here and continue next week. Thank you very much.
Thank you very much. Bye.